is going to be do about what the atmosphere actually is. So we're going to look at kind of how it developed potentially, the composition and structure of it. So with that in mind, what is that composition and structure? Well, first you got to understand the atmosphere covers the whole globe. So what happens in one part of the globe may impact the atmosphere in another. So they give a case in point of how the atmosphere contains different particles or different gases. And they show that dust is actually transported from the Sahara Desert in Africa all the way across the Caribbean and into central and southeastern US even. You can actually see on this satellite picture dust developing over the Sahara Desert and moving from that direction from the east towards the west. And dust can affect the air quality where it comes to. It actually increases algae blooms in the Gulf of Mexico, as suppresses tropical cyclones. So it actually plays a significant role in our weather. So weather can go very quickly from nothing happening to, oh, this is not a good day. So we're going to begin to look at that and how the atmosphere causes that to happen with weather. So when you look at the Earth from a scientific point of view, you think of the Earth as one complete system. In other words, there are volcanoes, there are ground. If I was teaching Earth science, we would be talking about each one of these atmospheric, these different aspects, but we're not. We're talking about one. So, but every one plays into the other. The hydrosphere, all the moisture on the Earth. We get rain. That is part of the impacted by the hydrosphere, the geosphere. Volcanoes, the ground with mountains. The mountains impact how the air flows. The biosphere would be us, plants. Guess what? Plants eat up carbon dioxide and produce oxygen, which we need to live. So, again, all of this is part of impacting the atmosphere. The atmosphere is pretty thin, too. You think about it, it's only about 20 miles, and 99% of the atmosphere is in that area. Think about the Earth and how big it is. This is like just a thin coating, like a peel on an apple or something that makes up the atmosphere. So the atmosphere is divided into two real parts if you want to think about how gases are. There's the hedosphere way up high in the atmosphere, which has all kind of different chemical gases in it. And then there's the homosphere where we live, which has nitrogen as the main gas and oxygen as the second, argon's next, and all the way down to carbon dioxide and other gases. And interestingly, if you think about oxygen being 25, almost 21% of the atmosphere, if you're at the Earth's surface, it's 21% of the atmosphere. If you're at the top of Mount Everest, it's 21% of the atmosphere. But the atmosphere doesn't have as many molecules in it when you get to the top of Mount Everest. So that 20% means it's very hard to breathe up there. Whereas down here on Earth, on the surface where we live, sea level, approximately there, 21% gives plenty of oxygen for us. And here are all the different gases, what they make up. Atmosphere also has aerosols in it. You may not see them sometimes when the atmosphere is pretty clear. However, there's other times that aerosols might make it kind of hard to see, like dust storms, volcano eruptions. Agriculture can produce a lot of dust sometimes. Uh, Ocean spray. All of these things put little molecules in the atmosphere, solid particles, and they kind of impact our visibility and how well we see. If you ever look at a sunset and you see it turning bright colors there without any clouds, a lot of that is from this dust and pollution. So water vapor makes up less than 4% in the lowest 1 kilometer of the atmosphere, and that is where most of the water vapor resides, in the lowest layers. But it's necessary for all the clouds and precipitation we see. And we definitely need carbon dioxide. Interestingly, the lower part of the atmosphere is warmer than it should be. It's a good thing, makes our life more comfortable, and that is due to carbon dioxide and water vapor. And we are going to get a lot more into that in the next chapter. There are primary air pollutants and secondary ones, which you can deal with. So when we study the atmosphere, we use what we call the scientific method. Every one of you at some point in some science class in school has talked about the scientific method. Put simply, we see problems, we see questions we have in the atmosphere, and we want to figure out an answer to them. We might start with an educated guess, try that educated guess and see if that actually works, make it a hypothesis, then test it. If it's correct, great, we've got an answer. If not, we'll reject that one and try another hypothesis. So when the final thing, the hypothesis, is accepted by the scientific community, then it becomes a theory. So I'm going to take you through a process we did. I was involved in with North Carolina State University a number of years ago. One of the biggest questions in the eastern U.S., on the east side of the Appalachian Mountains, is we want to observe why thunderstorms sometimes diminish when they come across the Appalachians at night and why sometimes they increase and get stronger when they come across the Appalachians at night. So we asked that question. That was the question we raised. Why does this happen? So we decided that, well, there's some parameters that may cause this to happen. So we looked at them and we started running tests on them. We discovered that, yes, some of these actually do have an impact. Others did not. So we developed a hypothesis. We had grad students working on it, analyzing it, testing it, and would look back at numerous cases where thunderstorms intensified or decreased. Finally, we just figured out that this is actually when it happens. We could look at these specific parameters. If they reached a certain threshold, thunderstorms tend to increase. If they were below that threshold, thunderstorms tended to decrease. We were able to utilize that and improve our forecasting on this side of the Appalachians. There are other scientific models that simulate the weather. We use conceptual models where we look at something, how does wind move? We're going to talk about some of those. We use graphical models. You look at those every day in a weather map. Physical models, there's actually miniature chambers where they try to create tornadoes or even clouds. And then there are numerical models. I did that in college where you actually use equations and data from current observations to forecast the weather in the future. And every one of these models has errors in them, inherent. They're approximations. That's why the weather forecasts are not perfect. But to make a weather forecast, we got to know what the weather is right now. One of the biggest tools in the United States is Automated Surface Observing Systems, ASOS. They're at just about every airport in the country. Why are they at the airports? Because planes need to know the weather before they take off or land. So it made sense to put these at every airport in the country so they'll know that. There are cooperative networks. These are people that even don't get paid. They do it because they want to, they love to look at weather, shall say. They will record max temperatures, daily precipitation, min temperatures, and all of this data will go into a big database to look at the climate. Climate is just an average of weather over long periods of time. There's also COCORAS, which is a volunteer network for measuring rain, hail, snow, even severe weather. Many types of that are reported into COCORAS. If you all were real interested and wanted to do it, they're happy to have more members. Radiosondes. They're a balloon with an instrument package tied on them. That's all they are. The balloons typically can make it up to 100,000 feet before they break, but that instrument package then has a parachute and comes back down to Earth. If the Weather Service is lucky, they'll get that instrument package back. It'll be refurbished and reused. Generally, that's not the case. Very few of them are found. But they're a way of telling the temperature, the pressure, the wind, how much moisture is in the air as you go through the vertical. Dropsondes, very similar instrument. Instead of a balloon taking it up, an airplane goes up and drops it out. These are used in many storms, particularly hurricanes, to determine the exact same things as the instrument drops down towards the ground. There are other things called remote sensing. So notice how I just said the dropsonde went up and went down. Well, when it went down, it was touching the air as it moved, so it knew what was happening right at that point. Remote sensing is, oh, I want to know what that air is like 10 miles to the east of where that dropsonde went down. So how do we do that? We have things called radar and satellite that are remote sensing. They send out pulses of energy, or satellites look at pulses of energy coming from the Earth, from the atmosphere, to determine what is happening. So, temperature profile is interesting in the atmosphere. Kind of divides the different levels. The troposphere, temperature drops fairly steadily. It may fluctuate a little bit, but it's going to tend to drop as it's going up to the top of the troposphere. Reach the top, it begins to warm. And it gradually warms again till we hit the stratopause. Then in the mesosphere, it's going to cool off again. And then we're going to hit another area where the temperature is going to significantly warm. So these are the different areas in the atmosphere. So another part of this all is the ionosphere and the auroras. In the ionosphere, we have solar winds impacting with our magnetic fields of Earth. Where that happens, it creates the magnetosphere, and that is where we get our northern lights or southern lights, depending on. And how powerful these solar winds are is how powerful and spectacular the light sequences are. And here you can see one. So with that, I wanted to go over here and show you. I've just given you an example here of numerical models. Talked about them. We're going to look through some of these. Every one of these is a different numerical model, and something is different about it. And down below it is different areas that we can see that new model in. So you can see there is a lot of different numerical models that meteorologists have access to. Another part of that is looking at, we'll call it a Stuvie diagram. All it is, down on the bottom is temperature, gets colder to the left, pressure drops in the vertical, and you can just see each one of these here, and you can get temperature and pressure plotted. And next to that is something called dew point. Dew point's a measure of the moisture in the air. This is Detroit, Michigan today. Has the winds right here. See the winds change and they change direction, increase further up you get. And finally, right up here at the very top, we're getting into the tropopause and actually moving into the stratosphere, where you can see temperatures are significantly getting warmer. That's the height of the stratosphere right now. Fairly high in the summertime. It's lower in the winter. We're going to talk about why that is. So this is what I wanted you to see with this. Let me know if you have any questions.